Let's see how to do the preorder traversal of a binary tree iteratively. To do this, we'll use a stack, and we'll start with an example that demonstrates the process. So here we have a simple binary tree and a stack. So we'll begin by pushing the root of the tree to the stack. And then we're going to set the current node to what is the top of the stack. So we're going to set current to 1. And we're going to pop the stack and print the current node. And then we see, does the current node have a right child? And if it does, we're going to push it to the stack. And then we check, does it have a left child? And if it does, we push it to the stack. So in this case, 1 has both a right child and a left child. Once we've done that, the reason why we first push the right child and then the left child is because we want the left child to be on top of the stack, so that we'll visit the left child before the right child, which indeed is what we want to do in a preorder traversal. So anyway, let's continue. We set current node to the top of the stack. We print it. We pop it from the stack. And then we check, does it have a right child? Yes, it does. So we push it to the stack. And then does it have a left child? So it does. We push it to the stack. Then again, we go to the stack and we set the current node to the top of the stack. We pop it from the stack, we print it, and then we check, does it have a right child? No, it doesn't. Does it have a left child? No, it doesn't. So we're done with the for. We go back to the stack, we set current to the top of the stack, we print it, pop it of course, and we check, does it have a right child? No, it doesn't. Does it have a left child? No, it doesn't. So we're done with the 5. We go back to the stack, we set the current node to the top of the stack, we pop it, we print the current node, and then we check, does it have a right child? It does, so we push it to the stack. And does it have a left child? No, it doesn't. So at this point, we go back to the stack, we're going to set the current node to the top of the stack. We will pop it, print the current node, and then check, does it have a right child? No, it doesn't. Does it have a left child? Yes, it does. So we're going to push it to the stack. We go back to the stack. We're going to set the current node to the top of the stack. And we will print it, and of course pop it. And then we check, does it have a right child? No, it doesn't. Does it have a left child? No, it doesn't. So we go back to the stack, but this time the stack is empty, so this indicates that we're done. So the final output is 1, 2, 4, 5, 3, 6, 7, which indeed is the preorder traversal of this binary tree. So let's actually implement this. So we're going to have a function called preorder, which is going to take the address to the root node, and we will return nothing, because we're just going to print the nodes. So we'll begin by checking whether the root is null, because if root is null, the tree is empty, so there's nothing to do. If root is not null, we will initialize the stack. And we push the root node to the stack. Then, while the stack is not empty, we'll set the current node to the top of the stack. We pop the stack. Then we print the current node. And we check, does it have a right child? And if it does, we're going to push it. So if current right is different from null, We push it to the stack. And then we check, does it have a left child? So current left is different from null. We push it to the stack. And that's it. So let's quickly run through an example to demonstrate that this actually works. So we have again the same tree, and we'll begin by calling preorder, passing in root 1. So we check, is root null? Root is not null. So we're going to initialize our stack st, and we're going to push root to the stack. And while the stack is not empty, in this case it's not empty, we enter the body of the loop. We're going to set current to the top of the stack, which is 1. We'll pop the stack, we print current, and then we check, does current have a write? So current arrow write different from null. The write of 1 is 3, so it's different from null, so we will push it to the stack. So stack push current arrow write. So that's 3. Then we check, does it have a left? So the left of current is 2. So it's different from null, so we're going to push to the stack 2. We go back to the condition, stack is not empty, we're going to set current to the top of the stack, which is 2. We pop the stack, we print current, and we check, does it have a write? The write of 2 is 5, so we push it to the stack, and we check, does it have a left? The left of 2 is 4, so we push it to the stack. We go back to the condition, and we set current to the top of the stack, which is 4. We pop the top of the stack, and we print current, so 4. Then we check, does it have a write? So the write of 4 this time is null, so we don't do anything. And the left of 4 is also null, so we don't do anything. We go back to the condition, and we check stack is empty, stack is not empty, so we set current to the top of the stack, which is 5. And we're gonna pop it. And we print current, and we check, does it have a write? The write of 5 is null, so it doesn't have. We check, does it have a left? No, it doesn't. We go back to the condition, stack is not empty, so we're gonna set current to the top of the stack, 3. We pop the stack, and we print current. Then check, does it have a write? Current write is 6, so we push it to the stack. And does it have a left? The left of 3 is null, so we don't do anything here. We go back to the condition, stack is not empty, we set current to the top of the stack. We pop the stack, and then we print current. And we check, does it have a write? The write of 6 is null, so we don't do anything. Does it have a left? The left of 6 is 7, so we push it to the stack. Then we go back to the condition, the stack is not empty, so we set current to the top of the stack. We pop the stack, and then we print current. And we check, is current write different from null? The write of 7 is null, so we don't do anything. Is the left different from null? The left of 7 is also null, so again we don't do anything. We go back to the condition. This time the stack is empty, so we exit the while loop and we're done. So let's analyze the time complexity. In this case, it will depend on how much work we do with the while loop. So if you look at the body of the while loop, every single run we print a node. And we know that every single node in the tree will be printed exactly once. So the body of the loop will execute n times, where n is the size of the tree. And if you look carefully, the amount of work we do inside is just constant amount of work. So therefore, the total work associated with the while loop will be O of n. So we can say that the time complexity is O of n. What about the space complexity? In this case, it will depend on the size of the stack in the worst case. So we know that initially we push the root to the stack. So stack has size 1. And then once we enter the while loop, we pop what's on top, and we're gonna push its right child and then its left child. So at this point we would have the right followed by the left. And the next iteration, we would again pop what's on top, which would be the left, and then we again push the right and then the left. And the next iteration, again, we would pop the left, which was on top of the stack, and then we push the right and the left. So as you notice, every single iteration, we pop one value and we add two values. So every single iteration, the size of the stack is incrementing by 1, and that 1 is simply the right child. So the question is, how deep can we go before we start popping the right too? So in this case, it will simply be the height of the tree. Therefore, we can say that the space complexity is O of h. You can find the link to the code in the description below.